Okay, then uh, welcome back to the week 9 of the problem solving session of the course for the course Fluid Mechanics and its Applications. Okay, so this week we will be dealing with a very important as well as interesting and conceptually rich topic of approximate solutions to the Navier-Stokes equation. Okay, so the first question itself arises like, why approximate? Like, why to deal with approximate solutions, right? Because it seems contradictory, like as as in the previous sessions we have solved some exact solutions, and they were, like as I mentioned at that time, like they seem to be quite helpful, even though they are very simple geometries uh, such as the Hagen-Poiseuille flow. That means fully developed flow in a pipe. Hagen-Poiseuille flow, plain Poiseuille flow, fully developed flow between two parallel plates. As well as coed flow. One of coed flow in which one of the flow is between two parallel plates, in which one of the plates is fixed and another plate is moving. Okay, so even for these kind of problems we were getting exact solutions, and we were after because of the geometry and the certain assumptions that we made, such as the fully developed flow or laminar flow, steady flow, like all these assumptions, we were able to simplify the equation considerably and then get the solution. And these solutions were, as you might have noticed, like quite fruitful, as I may say, like they helped us to get a very proper insight to the problem, even to the problems that were not exactly Hagen-Poiseuille, plain Poiseuille, or coed flow, right? For example, in the case of pipe flow, even though most of the times we cannot exactly consider them as a fully developed flow, but as I also mentioned, that for most of the length of the pipe, like since usually the pipes are usually very long, or the length to diameter ratio are too high, like so usually the length of the diameters are considerably much higher than the diameter of the pipe. So for certain up to certain length, or after certain length, we can ideally assume the flow to be fully developed. So there were some assumptions that we made, but these solutions, that the exact solutions of the Navier-Stokes equation, seemed quite fruitful and were really helpful. They were really helpful. So the question arises, why to deal with approximate solutions, right? So the answer lies in itself in the fact that the problems that we have chosen, the exact solution that we got, were for very simple geometries, extremely simple geometries. Okay. Which is not usually the case most of the times, right? In our day-to-day application or day-to-day engineering applications, we don't usually deal with such simple geometries, like always, like not always, obviously not that complicated, not also very complicated, but not also that simple. So the very applicability of the exact solutions comes into question, like if the geometry is changed, and obviously the solution would also change. That's fine, but again another important question arises, that the approximation itself, or I must say limitations to approximations. Yes, the approximations that we made, that the flow is steady or fully developed, or certain terms are negligible, like effective terms cancel out, like these assumptions that we made, that we crudely or directly stated before even solving the problem, the question arises like up to what extent or up to what limit these approximations are valid, right? Like it is not, it's not the case that this approximation will always be valid, right? We just said upfront before starting to solve the problem that these are the assumptions that we made, and we assume that these are valid, and then we are trying to solve the problem, and then we are giving the solutions. And only after applying those assumptions and considering that those assumptions were true throughout the solution, then only we said that yes, these are, if these assumptions are true, then this is the final solution, or this is the exact solution of the Navier-Stokes equation, right? Because eventually we found out that all the governing equations that we solved were eventually simplified to a linear homogeneous, most of the times homogeneous, linear homogeneous ordinary differential equation, which was quite easy to solve. Okay, so the main crux or the main point that we want to understand by today's session, that is the approximate solution of the Navier-Stokes equation, is that up to what extent or up to what limit the approximations that we made for the exact solutions were valid, right? Up to what extent we say that this certain solution or a particular solution is valid, right? There must be a value of a certain parameter. Let's say Reynolds number, that we have already introduced what Reynolds number is. That is basically the ratio of the inertia force or the viscous force. So if we say that if Reynolds number is high, if Reynolds number is very high, like if we say the Reynolds number is very high, say consider one assumption that approximation that Reynolds number is very high, then I can say that my particular solution is valid. Then my particular solution is valid, or particular form of the solution is valid. But if the Reynolds number is not high enough, then I cannot say my solution would exist. Okay, so we will look. So in today's session we will basically look upon such kind of assumptions or approximations that we make, so that our solutions remain valid, or the approximation or the extent to which the parameters have to be considered or parameters have to be taken, so that our solution will remain valid. So this is the very crux or main focus of today's session. Okay, so let's start with it. So again, as I said, to understand these concepts or understand the very concepts or approximations, we need to recollect all the concepts that we learned till now. That is the governing equations, that is obviously the Navier-Stokes equation, then the concept of scaling, non-dimensionalization. So all these concepts I expect that we all have discussed thoroughly. We also have solved some examples, problems, so that we know now what the scaling, how the scaling has been done, what are the characteristic length scales, and how important role they play while non-dimensionalizing certain parameters or variables in the governing equations. Okay, so I think I will not have to repeat the very definition of the characteristic variables. So I will start or continue the session with an assumption that we all know very well what the characteristic variable means and how they help us to non-dimensionalize our governing equations. Okay, so keeping that in mind, so for our first case, this case again has been dealt by Professor Gupta in his lectures, but just for our understanding, I will be dealing with the same example. So consider a flow over a cylinder. Okay, it's a cylinder placed in a flow field, so it's just a cross sectional area, or you can consider it a side view where there might be a depth of the cylinder within the page, and there is a flow over the cylinder. Okay, so this is the direction of the flow. So flow will occur above this cylinder. Okay, so again the governing equations remain the same, right? The name, as we know, for all kind of fluid flow problems, given that the fluid is Newtonian, the governing equation is the Navier-Stokes equation, right? So so we seek to non-dimensionalize our variables or flow variables. So in this case, if we consider that the along the z direction or along the y direction, the length is infinite. So we can assume that, or we can consider that the flow through each and every cross section would remain same, right? So the variation along the y direction becomes negligible, right? We applied the same example, or same approximation in the case of flow between two parallel plates, that the dimension along one of the coordinates is so large that the variation along that particular coordinate direction can be ideally neglected. Okay, so keeping that in mind, if if the flow or if the length along the y direction is very large or considerably large, so variation along that direction can be ideally neglected. Okay, so keeping that in mind, so we are only now dealing with only two coordinates, the x and the z coordinates. Okay, so we non-dimensionalize the x and z coordinates with the diameter of the cylinder. So that will be our characteristic length scale. Again, since the flow, the incoming flow or the incoming flow is a function of time, so we need to non-dimensionalize the, and it ideally tells us that the flow should be unsteady. Okay, since the incoming velocity field is itself an unsteady velocity field, so the flow, it will inherently become unsteady. Okay, I'm not considering like what are the conditions in which the flow could be treated as steady, but inherently, just for the ideal case, we have to consider the flow to be unsteady. Okay, just for the start or for the timing. Okay, since the flow itself, the incoming flow itself is unsteady, so the flow or the flow that would develop over the cylinder would be unsteady. Okay, so again, then there might be certain assumptions or value of the parameters that we can choose to consider this flow to be to make this flow steady. Okay, like for example, like for a value of certain parameter, we can say that if the value of this parameter exceeds this value, then we can say that the flow is ideally steady over the cylinder. Okay, but for now we have to consider the unsteady parameter. Okay, so that's why we need to non-dimensionalize the time parameter as well. So we non-dimensionalize this time parameter with a value tau. Okay, for the u and w velocity component, we non-dimensionalize it with the amplitude of this velocity, incoming velocity. Okay, so it basically tells us the incoming velocity is a sinusoidal velocity profile. So the amplitude of this velocity can be taken as the scaling parameter for non-dimensionalization of the u and w velocity component. Okay, so the non-dimensional for the form of the continuity equation is very simple. It's basically the same. So as it is homogeneous and only contains single terms, all the non-dimensional parameters that can be that come after non-dimensionalizing the governing equation can be taken as a constant and be transferred to the right hand side. So the equation remains the form of the continuity remains exactly the same, but just the difference is that now the velocity and the nabla operator is non-dimensional. Okay, now we take our momentum equation. So we non-dimensionalize our momentum equation. So I won't go to the detailed step of how these terms have been considered. So the steps, I guess, would be quite clearly explained by Professor Gupta in the lectures. But simply speaking, if we consider, say, this, I will just take the example of the first case. Okay, so for first term. Okay, so if we consider this v, so it can be considered as since you know the non-dimensional term, say v star should be v by v naught, and it basically implies v is equal to v star naught into v star into v naught. Okay, so given so if we substitute v with this parameter here, this value here, we get, since this is a constant, it will come out of the derivative, so we get this term. Similarly, for time term, if we substitute t is equal to t star sorry, t is equal to t star into tau, so tau would come out and the t star term would remain within the differential operator. Okay, similarly we do the same thing for all the terms in the governing equation, and here right now, similarly as we see, we do not know how the pressure scales, so we take a non-dimensional pressure term P naught to scale the pressure term. Okay, so see, pressure is a very interesting term in the Gauss equation. Okay, we will deal with it in the, as we go toward along this go along with the session. So we will see how the actually the pressure scales. Okay, so this is a very interesting term and interesting concept behind it. So I'll tell you that. But for right now, we can just say that the pressure scales as a non-dimensional scales as P naught in our current context. Okay. So after non-dimensionalizing, we get certain coefficients for each term. Okay. So for the first term, we get the coefficient as d by v naught tau. Okay, this is the first coefficient. Then for second, we get p naught by rho v naught square. Okay, this is the second coefficient for the pressure gradient term. Then we get gd by v naught square for the body force term. Minus sign just signifying the direction of the body force term. So I guess this will be wrong because then I'm not using the k cap as it was used in the lecture. So I prefer to use the body force term and then decompose it accordingly. So I will just keep it as plus gd v square by v naught. Because I don't know the direction of the body force term. So if and only if we take the direction of the gravitational force to be in the negative z direction, then only I can take as minus k. But that both are correct. So just for my convenience, I have chosen this. Okay, so there's no big deal about it. And finally, for the viscous force term, we get the coefficient as mu naught by rho v naught v. Okay, so by now I feel like most of these coefficients are now well known to you. Like these are more very popular non-dimensional numbers. So we will eventually see what they signify. So just a moment. Okay, just a moment. Sorry for the delay. So this is the non-dimensional form of the Gauss equation, and this is a boundary condition. Okay, so boundary condition, I guess it's again well explained in the lecture, so I won't go through it. So now, as I told you, these coefficients that we get for these particular terms signify some certain very popular non-dimensional numbers. Like so, we see that the first term gives signifies the Struhal number. So Struhal number, or which is usually denoted by as St, is usually denoted, if we look in the definition, it's usually represented as Fl by U. Okay. So where L is the characteristic length scale, U is the characteristic velocity, and F is the characteristic frequency of oscillation of the velocity profile. Okay. So usually you see that this kind of the Struhal number comes into picture of usually comes into picture in the case of oscillatory flows. Okay, so again, since in this case the incoming velocity profile or is a sinusoidal velocity profile, so it has an oscillating nature. Okay, oscillating nature inherent to it. That's why the concept or the applicability of Struhal number fits rightly in this context. Okay, and that's why the validity of the existence of Struhal number as one of the parameters in this Gauss equation seems rightly seems completely correct. Okay, so that's not at all deviating from the concept of the not deviating from a fundamental concept that we learn. Okay, so that's completely fitting to the concept. Since the flow is there is a oscillating nature to the flow, so the concept of Struhal number completely fit in this problem. So, but you can see here instead of frequency, you have a time parameter, non-dimensional time. So, obviously, since we know frequency would be the inverse of the time period, so you can ideally consider this tau as a time period of oscillation. Okay, so that's the way to look into it. Okay, so and for the non-linear advective term, you see there is no coefficient. The coefficient is 1, so that's fine. Then for the pressure term, you see is actually the inverse of the Euler's number. Okay. Similarly, for the gravitational force, so the body force, you can see that the coefficient is the inverse of the square of the fruit number. Okay. Fruit number, flout number, like whatever you say, it's correct. But as I have learned and seen or heard, it's usually pronounced as fruit. So I will take that for my case. But you can take tell it in whatever way seems comfortable to you. Okay, that's fine. Just I explain it so that you do not get confused. Okay, so it's for my case I will define say it as fruit. Okay, FROUD, fruit number. Okay, and finally for the viscous term, it's a very popular non-dimensional number. It's a Reynolds number, basically the Reynolds number. So the coefficient is the inverse of the Reynolds number. Okay, so now you can get an idea, like the how the concepts of non-dimensionalization or scaling or even the Buckingham pi theorem that we learned when in dimension analysis comes into picture, like gives us an idea, like how to non-dimensionalize the government equation first, that is being learned through the scaling analysis and the understanding of the non-dimensionalization. Okay, then secondly the Buckingham pi theorem. Okay, see Buckingham pi theorem, as I mentioned, is help us to know for a particular flow, experimental flow analysis, what are the group of pi numbers or non-dimensional numbers that play a role in defining the physical problem, or helps us in analyzing the given problem. Okay, so similar to that, since we know every fluid flow problem or every fluid mechanics experiment would be governed by the Navier-Stokes equation. So once we non-dimensionalize the Navier-Stokes equation and get the pi terms related to it, so this gives us an idea that since for a particular problem the non-dimensional parameters are the Strohal number, Euler's number, fruit number, and Reynolds number, so we get an idea that for the proper analysis or for the proper understanding of the given problem, that is basically the flow over cylinder, these non-dimensional parameters, that is Euler's number, fruit numbers, Reynolds number, and the Strohal number, would be important. Okay, so these are the non-dimensional parameters that would govern or fully determine the simply say they will govern the problem. Okay, these are the non-dimensional numbers that will govern the problem. But again, you may ask that whether these are the only non-dimensional are these are the only numbers or non-dimensional numbers that will come into picture whenever we non-dimensional Navier-Stokes equation. So the answer is no, it's not the case. Given that our particular geometries had particular characteristic length scales, time scales, and velocity scales, so because of that only we got certain non-dimensional numbers, okay, non-dimensional numbers that govern the problem. So even though the governing equation remain the same, the variation in the characteristic scales or the characteristic scales would result in the existence of different non-dimensional numbers. Okay, so I will give you an example. So in the case of say electrostatically driven flows, okay, or electrophoresis, okay, in those cases what happens is that the body force term, this is ideally this term, okay, these terms, instead of being the gravitational force, becomes the force becomes force due to electrostatic, becomes electrostatic force. Okay, right. So to non-dimensionalize this body force term, we need to use different scaling parameters, right? So the choice of or choosing different scaling parameters for the body force term would again result in the existence of a different non-dimensional number. Okay, so again instead of fruit number, you might get different non-dimensional number that would govern that particular kind of problem. Okay, so that's why the choice of the length scales as well as the driving force or the in this particular example, it is especially the body force term, also plays a very important role in determining the non-dimensional numbers that govern the particular fluid flow problem. Okay, so that's why I wanted to emphasize upon it, like how the uh, characteristic length scales, the choice of length scales and the driving force terms can help us to determine the non-dimensional parameters that govern the problem. Okay, so it's not same in all the cases. Okay, again, so it varies from problem to problem. Okay, so I hope it was helpful. So let's go into the case of this following example. This is the case of oscillating boundary problem. Okay, so it's basically the it's basically a, if you consider this geometry, so in this case basically it is a flow between two parallel plates. So but in this case one of the plates is considered to be stationary and another plate, instead of moving in a particular direction with certain velocity, that is basically the case of a coil flow, it oscillates along the x direction. Okay, just since the current coordinate system tells that the x direction is along this side and y direction is along this side. Sorry, I'm right properly. So x and y direction. So the current, so the problem states that the one of the plate remains stationary. Okay, I'm sorry. So just for kindly wait for 1 second. Okay, so there is a issue in internet connectivity. So, sorry for the delay. So, there was some internet connectivity issue. So, that's why it is. So, forgive me for that. Okay. So, yes. So, as I was explaining, the current scenario, the case of oscillating boundary problem, uh, essentially tells us that in this case, similar to the case of flow between two parallel plates or the quiet flow, the fluid is confined between two parallel plates, where the again the variation or the length of the plate along the z direction is very large compared to the gap. This gap between two parallel plates, that is basically B. Okay. So it essentially tells us that any gradients or any variation along that particular coordinate can be taken to be essentially 0. Okay. So that's why so any variation along the z direction is taken to be 0 in this case. Okay. And differing from the coed flow, the thing is that the one of the plate remains stationary, but the other plate, instead of moving in a particular direction at a certain velocity, it oscillates along the x direction with a certain time period. Okay. So that's what the problem basically means. So the plate will be oscillating to and fro in the x direction. Okay. So that would generate a certain flow field. So we will see how to model or analyze that particular flow. Okay. So in this case, the unsteady forces, obviously, since the velocity field is time dependent, or I must say, or the driving force, which is basically the plate, the motion of the plate is unsteady, so that will generate a velocity profile. So that itself is unsteady. So the unsteady nature of the problem is inherent to the problem. Okay, so that cannot be disregarded. But as I again mentioned, that there may be some certain parameters or assumptions or approximation that can be made that would result in taking or considering this problem to be ideally steady. Okay, so that we can do, but for right now, at the start itself, we cannot disregard the unsteady nature of the flow field. Okay, so as we have seen here, the unsteady forces can be estimated as mass into acceleration. Okay, so the mass basically is the mass of the fluid. So the characteristic length scale would be so the characteristic rho c denotes the density of the fluid, and LC denotes the characteristic length scale. Okay, so LC cube into acceleration. This is basically the velocity divided by time. Okay, so we get the unsteady term. The unsteady term would scale as rho c LC cube VC divided by DC. Okay, it's not exactly equal to this, but we're just trying to say that the acceleration term, if that exists in the flow field, would scale as this value. Okay. Similarly, the viscous forces can be estimated as we know, for Newtonian fluid, the shear stress, the shear force can be calculated as mu dou u by dou y. Okay, and if this force, then we consider the area. Okay, so so details. So to find how the shear force scales in this particular case, we take the viscosity of the fluid, that is a fluid property. So that would have the viscosity will scale as mu itself. The area would scale as the square of the length, so into LC square, and the velocity gradient will scale as VC divided by LC. Okay, I guess it's quite self-explanatory, so it's very simple to understand. So if we do that, we get that the viscous forces scale as mu LC into VC. Okay. Now, if we now put the values of the characteristic length scales of parameters in these variables, so we take LC as B. Okay, that's quite understandable. So since, like, if we consider that the plate is quite long along the z direction, and also if we consider that the length along the x direction is considerably larger or longer than the height of the or the gap between the two parallel plates, then we can ideally understand that whatever changes or whatever interesting changes in the physical changes, sorry, or I must say whatever interesting flow physics that would occur, that would be confined within this length. Okay, I'm not saying there's no change or no interesting change going on along the x direction or z direction. Okay, that if you look into it, there might be there, but since the length scale is much smaller compared to the z direction and the x direction, so whatever changes in the flow physics that takes place because of the oscillation of the plate is quite amplified within this region, so that can be easily seen or observed or even quantified within this region. So that's why the characteristic length scale for this problem is chosen to be the depth or the gap between the two parallel plates. Or I must say, like, the very definition of characteristic length scale, as I said, was the length scale along which there is a considerable change in the velocity field or the pressure field. Okay, since we are not there is no applied pressure gradient in this particular flow problem, so we can say that the length scale along which there is a considerable change in the velocity field. So, and that length scale can be termed as the characteristic length scale. Okay, so that's why we choose B as our characteristic length scale. And then V characteristic velocity can be chosen as the amplitude of the oscillation of the plate, so that could be taken as V0. And finally TC could be taken as very interesting one again. TC can be taken as the 1 by the frequency of the oscillation of the plate. Okay, since the dimension of 1 by omega would give us second, so dimension of 1 by omega would give us second, so we can take the characteristic time scale for this particular problem as 1 by omega. Okay, so these things, how to choose the characteristic length scales, I guess, as I said, comes from experience. Okay, like we solve different kind of problems, see different kinds of experiments, so this comes from experience. Okay, in future it might happen that for certain problems that are quite new or quite being analyzed for research at the present day, so it might happen that the characteristic length scale that a particular scientist chose for a particular problem would be different from the characteristic length scales or velocity scale that a scientist that will solve the same problem 50 years later. Okay, so the technology or the knowledge pool would be different 50 years from now, so they would be able to choose better or more accurate characteristic length scale or velocity scales that would help to non-dimensionalize the governing equations even in a far more better way. Okay, in a far more better way, that would help in analyzing the problem in a much more efficient manner. Okay, so that's the beauty of fluid mechanics itself, I can say, but that's the beauty of the subject. Right? It's not limited to a particular researcher or the knowledge of a particular researcher or the problem itself. Okay, it also depends on how one looks at the problem. Okay, so this is exactly what we will see in this example itself, and also the final problem that we solve for today's session, that is basically the boundary line analysis, like how the perspective of the researchers or the scientists who solved the same problem at different time periods resulted in different conclusions. Okay, so that's the beauty of the subject. So we will see, and we can even see that example right away in this current problem itself. Okay, so now we get that the unsteady force term now scales as rho b cube v naught omega. Okay, and the viscous term scales as mu b v naught. So now the ratio of the unsteady term to the viscous unsteady force to the viscous force gives rho b square omega by mu. Okay, and this determines the relative importance of the two types of forces. Okay, so now you may ask, like, why we are scaling only these two forces. Okay, so the thing is that if we consider the governing equation, okay, like, I guess I will show you here. If we consider the governing equation, so now if you look at the continuity equation, okay, so from that we get that dou u by dou x plus dou v by dou y equal to 0. Okay, that's the continuity equation. Okay. Now, if we see, I told that the unsteady term would go out even if the flow is unsteady, but if the flow is incompressible, the unsteady term would go out. So for the incompressible flow, this is the governing equation. Okay, this is the governing equation that we solve. Okay. So again, I am sorry. So one more important assumption that we take for while before solving this problem is that rho is constant. Okay, the density remains constant. The flow is incompressible in this case. Okay. But that again ideally should come into that should ideally come to the mind of the researcher or the one who takes the problem, as the fluid is, if we take the fluid to be water, then also the water itself is highly incompressible in most of the scenarios, and again the flow velocity itself is in a is very small or within the subsonic range. Okay, so that's why the incompressible nature of the fluid goes out. The compressible nature of the fluid goes out of the context immediately. So, but then also, like, we need to check again and again. So that's right. So from the continuity equation, we get that dou by dou x plus dou v by dou y equals 0. Okay, and we see that since the flow is essentially one dimensional, so the v component of the velocity is 0, so we get that dou v by dou x equals 0. Now, if we now consider the momentum equation, dou v by dou t plus u dou v by dou x, and as I told, since the flow is inherently one dimensional, so the v and w velocity component would be 0, right? So we would get so only the first term of the convective acceleration part will remain. So we get u dou v by dou x is equal to minus 1 by rho dou p by dou x plus nu dou square u by dou x square plus dou square u by dou y square plus dou square u by dou z square plus rho dx. Okay. So from the continuity equation we get that dou v by dou x equals 0. Okay, this is equal to 0. Again, since there is no applied pressure gradient as I told, so the pressure gradient term would go up. Okay. Then since dou u by dou x is equal to 0, then dou square u by dou x square would also be equal to 0. Okay, so this will go up. Again, since as I told, the variation along the z direction is considerably very small, so we can take dou by dou z of any parameter as 0. So dou square u by dou z square would be equal to 0. Okay, and since there is no body force term that we are considering in this case, and also there is no point of considering the body force term along the x direction for this particular problem. So rho bx equal to 0. So we are only left with two terms, that is the unsteady term dou v by dou t and the viscous force term. Okay, this new dou square by dou y square. So since there are only two forces that there are only two terms that exist in the governing equation, which themselves represent two different types of forces. That's why we are comparing the relative magnitudes of these two forces and how they scale to see which of the two forces dominates the our flow field. Okay, so as I mentioned here, the ratio of the ratio rho b square by mu then determines the relative importance of the two types of forces. Okay, so now if omega is less than mu by rho b square, the unsteady effects are very small and may be neglected in comparison with the viscous forces. Okay, why? See, we have I will just tell the example. So after that, I guess you will understand how I take the approximations. Okay, so just to keep that in mind. So if f unsteady by f mu is equal to rho b square omega by mu. Okay, so how we got it? I guess you just take the ratio of these two terms, you will get the same result. So now if we say that these are, if we say that this scales as 1, okay, these are almost equivalent. If this scale is 1, then we say that rho b square omega would scale as mu. Okay, just take mu here. Okay. Now, I'm sorry. Now, if I take these two terms in the denominator, so we can write omega would scale as mu by rho b square. Okay. So now, if I say, if I now try to consider omega as a parameter, that so ideally what I'm trying to say is that now this formula equation can help us to ideally represent the relative magnitude of the two types of forces uh, based on the value or the value of or the scale by which our omega varies. Okay, so now if omega is omega is very small, okay, omega is very small, it already tells us that uh, the viscous effects are considerably larger. Okay, so it tells us that if omega is smaller than mu by rho omega square, then the unsteady effects are small and may be neglected, and may be neglected in comparison with the viscous forces. Okay, so I hope it was clear. Okay, so we are just playing with the values. We took this term in the denominator, and then we consider the relative value of the omega to determine the relative magnitudes or relative value of the two types of forces. Okay, so now if omega is large, so it essentially tells us that mu would be large. Okay, if mu is large, it essentially tells us that the viscous effects are much larger compared to the unsteady terms. Okay, so that's why these unsteady effects can be neglected in this particular approximation. Okay, so once the unsteady terms are neglected, the governing equation would require that the viscous forces to be zero. Okay, so what it essentially tells us that now if I say that the unsteady effects, if these terms are if these terms are almost equal to zero, so it essentially tells us that the viscous forces term or viscous forces terms would now be equal to zero. Okay, so our governing equation would simplify to dou square Vx by dou y square is equal to 0. Okay, or dou square by dou y square equal to 0. I mean this term. Now again from the continuity equation we got that dou u by dou x equal to 0. So it essentially tells us that u is a function of y only, right? So we can convert this partial derivative to complete derivative to get d square vx by dy square is equal to 0. So this governing equation again very simple. It's only a second order ODE, homogeneous ODE. So quite easy to solve. So the governing equation simplifies. But see how the simplification was achieved. Okay, see for the coed flow. So for example of coed flow, we told that the flow is steady. We just inherently or upfront tell that the flow is steady, but that's not usually the case, nah. So that usually not the case. So but in this example we have like very properly or methodologically explained that how the unsteady terms or when the unsteady terms can be neglected. Okay, so we told that given the case if the frequency of oscillation is less than this value, the frequency of oscillation is less than the value, that is mu by rho b square, then I can tell that the flow field that develops within this confinement, within these two parallel plates, can be taken to be or steady, or I must say that's not the right way to put it. Or what I can ideally say is that given that omega or the frequency of oscillation of the lower plate is less than mu by rho b square, then the unsteady effect that is being generated because of the oscillation of the lower plate can be neglected. So that's the right way to put it. Okay, the flow is not steady. That's obviously not possible, right? Because there is a oscillation, and it itself tells us that there is a time dependency in the velocity profile. But what helps in simplifying the problem is that given that the certain parameter, in this case that is the frequency oscillation, is less than or greater than some particular value, right? Then the unsteady nature that is being generated because of the oscillation of plate can be essentially neglected. Okay, it's not zero, but it can be essentially neglected, which gives us, which tells or which signifies the concept of approximation, that we are approximating the solution given that a certain parameter or certain value of certain parameter is within or within certain range. Okay, so that's what I was trying to tell or trying to explain or correlate from the beginning, like how the approximate solutions take into consideration the value of certain value of the parameters that helps in approximating the solution. Okay, you cannot say upfront that the solution is the governing equation is this or governing equation is that, but we need to consider, we need to give a certain value to a particular parameter, that would help us to simplify our governing equation, and then we can tell that within this limit, within the limit that omega is less than mu by rho b square, our governing equation would be this for the entire geometry, for the entire domain. Okay, so that's the conclusion. So now given that this is our governing equation, so now and since since the solution of this governing equation is already known, so we will not go in and go on to solve this equation. See, the solution is known. That will basically be like, if I look into it, so it will be Vx would be c1. Let's just solve it, right? So if we integrate it once, so we will get dou Vx by dou y is equal to c1, right? So if we integrate it again, so we get Vx would be equal to c1y plus c2. So there is some there will be some linear velocity profile, right? So the velocity profile will be linear, as we know, right? Given that, again and again emphasizing, given that omega is less than mu by rho b square. So this will be the form of the So this will be the form of our velocity profile. It would be linear, given that this is the case. Okay. So we will not now go on and solve the governing equation, because it's quite simple and can easily be solved. So solution we already know. Only the boundary conditions will change. So we need to apply the boundary conditions accordingly. Okay. So but let's see what this approximation implies to our solution, right? What this approximation signifies. Okay. So we take this parameter that we got, mu by b square. So basically what we got was omega is less than mu by rho b square. So if we take mu by rho as nu, which is the kinematic viscosity, so we can write omega is less than mu by b square. So now what we are telling is that we define b square by nu as a penetration time or tau. Okay. So given the definition, we can say that if the time period 1 by omega of the oscillation of the lower plate is much more than the characteristic time scale, then the motion of the plate is so slow that the unsteady inertia of the fluid can be neglected. Okay, see, this is very important observation or conclusion. Okay, see, omega less than nu square by nu by b square essentially tells us that omega is less than 1 by tau. Okay, if we take this as tau, then omega less than tau. So what they are claiming here is that if the time period 1 by omega of the oscillation of the lower plate is much more than the characteristic time scale, or if the frequency of the oscillation of the lower plate is much lower than the characteristic frequency of the motion of the plate. I'm sorry again. So here what they're trying to say is that if the time period of oscillation of the lower plate is much more than this characteristic time scale, okay, this characteristic time scale, this is basically this, or in other words you can say if the frequency of oscillation of the lower plate is much higher than this characteristic frequency, other than characteristic time scale we can take characteristic frequency, then the motion of the plate is so slow that the unsteady inertia of the fluid can be neglected. Okay, so again I will tell you after we read all the points, so that would be easy to explain. Okay, or alternatively we can consider nu by omega as the penetration depth LP. Okay, penetration depth LP defined as a distance through which the viscous effects penetrate in time 1 by omega, which characterize the motion of the plate. Okay, so let me just I guess it was pretty self-explanatory, but let me just explain it once again. Okay, so let me go back to the diagram. Okay, so what they are trying to say is that if omega is less than nu by b square, okay, or b can be taken as square root of nu by omega. Okay, so this is a conduction depth and this is a characteristic frequency. Or ideally I can also write tau is equal to b square by nu. So if omega is less than nu by b square, it basically means that tau is greater than b square by nu, where b square by nu represents the characteristic time scale. Okay, the characteristic time scale of the oscillation of the plate. Okay. Then again you may say, what does the characteristic time scale mean? So the characteristic time scale essentially means that time scale essentially means that the value of the time, or the value of the time period within which there is a considerable change in the flow parameters. In this case, since we are not considering pressure, so in this case the velocity field. Okay, so or you can also say that the value of the time scale or a time period in which there is a considerable change in the velocity profile. Okay, so if tau is greater than b square by nu, so it basically means that if this t, or so it can also be written as v naught sine t by time. So if this tau is much larger than this characteristic characteristic time scale, so basically means that this plate will oscillate very slowly. Okay, it will oscillate very slowly. So the I guess there's a very good animation by in Professor Gupta lecture. So I think I should go a bit fast, but let's just try to understand it in as fast as we can. Okay, so I don't think we have time to emphasize it again and again. So let me just tell it once. So I hope it will be enough. Okay. So it means that if tau is greater than b square by nu, so the period of oscillation of the plate is such that once the plate moves here, okay, the plate will move here, the fluid that is being attached to the plate would try to move in this direction. Okay, try to move in this direction. Again, like after the plate has moved to its further extent, say, so the velocity profile has taken this shape. Okay. After that, again, like when the plate starts to move in this direction, the fluid molecules or the fluid within this confinement would behave in such a manner that the velocity profile would be generated in this fashion. Okay, so this variation of the velocity profile is not, what to say, hampered or modified because of the oscillation of the plate. Like essentially we saw that this velocity profile, this linear velocity profile is in the case of a coil flow where the plate moves in a particular direction. Okay, in particular direction. In that case only we get a linear velocity profile. But even though in this case, even if the plate is oscillating, this period of oscillation is so high or so large that the that the variation that could have taken place in the velocity profile because of the oscillation of the plate is not observed in this particular case. Okay, so if the plate was oscillating in a very higher rate, in a very faster rate, so we can essentially assume that the velocity profile should have been somewhere like this, right? It should go here. Now the plate again returns back, so the velocity profile should go there. Again the plate moves in that direction, so velocity profile should go here. So there should have been some wiggling in the velocity profile. But since the time period of oscillation is so large that the velocity profile has enough time to adjust to the changes that has been generated because of the motion of the plate, and that's why it inherently generates only linear velocity profiles, and the wiggles that could have been generated because of the higher time periods because of lower time period of oscillations is not observed. Okay, so that is the conclusion that we get. Okay, or in a defined manner, what we can say is that if beta is Okay, so what we saw here. Yes. Okay. So let's go back. We sure like yes. Sorry. Uh, Similarly, so okay. So now if we take beta here, so what we can write is that beta is less than mu by omega. So again, if this beta, this depth, this gap between the two parallel plates is, if it is smaller than this length scale, okay, this nu by omega, which is the characteristic length scale of this for this particular flow field, then if beta is less than nu by omega, so it essentially tells us that the depth of penetration is this depth beta is less than the depth of penetration. So what ideally means is that, like, if this plate moves in a particular direction, that would generate a particular effect that would have a effect or a penetrating effect to a particular length, okay, to a particular distance. So now if beta is less than that distance, so I will just represent it by this line. So if we say the penetration depth is, say this is equal to mu by omega. So if the motion of the lower plate causes a penetration depth of, say, LP is equal to nu by omega, which is greater than the greater than the gap between the two parallel plates. So essentially tells us that the effect or the effect of the oscillation of the plate is being felt throughout the domain. Okay, since this is lower than this one, so the effect of the motion of the plate is being felt throughout the domain, throughout the flow domain, or throughout the gap between the two parallel plates. So the entire flow domain, that is the fluid molecule from here to here, all the fluid molecules sense the effect of the motion of the plate, and also has enough time, that is being represented by this equation, and also has enough time to reorient themselves in a manner that would result in the generation of a linear velocity profile because of the motion of the plate. Like, they do not need to rearrange themselves within or in between the in between the length or depth b, so that they could follow follow the oscillating motion of the plate. It's not required, since the time period of oscillation is so low that they have enough time to orient themselves in this direction when the plate moves in this direction, and again easily orient themselves in this direction when the plate moves in this direction. So I guess I tried to explain it as much as possible, but I guess this is quite well understood when we look at the animations, okay, animations by Professor Gupta. So I suggest that you go into that video lecture. Okay, so now let's just look into the different, let's just take a different case. Okay, so now the other limit is, like, right now we consider that omega is less than mu by rho b square. Okay, this is the first case that we consider. Now the second case will be just the opposite, that omega is greater than mu by rho b square. Okay, so this is what we considering here. So the other limit is omega is greater than mu by rho b square. Now that leads to a very serious complication. Okay, so what happens is that now we the very basis of approximation was that that is the principle of small cause producing small effects suggests that we can neglect the viscous procedure. It basically tells us that if the scaling of certain parameters or certain forces are small in the governing equation, then we can ideally neglect those terms, or neglect those terms in the equation, right? So it essentially tells us that if omega is uh, greater than mu by rho v square, so just 1 second. Okay, yeah, yes, that's fine, that's fine. Okay, sorry, so I'll just okay, it's a bit confusing sometimes, so I'm sorry, like I'm going way to it for too much. So now, okay, so if now if omega is greater than mu by rho b square, so it essentially tells us that the frequency of oscillation is now greater than some certain value. Okay, so that is basically the characteristic frequency in this case. So if the frequency of oscillation of the plate is greater than the characteristic frequency, so it essentially tells us that now the viscous forces are can be neglected in with respect to the unsteady force terms. Okay, unsteady term in the governing equation. So it will essentially tell us that since the viscous force term will be neglected, so we will be left with this equation. Okay, dvx by dt is equal to 0. So now this equation, what it signifies is that there is no variation in the velocity component with respect to time, but which is not the case. Okay, so this equation is now not able to capture the essence of the problem, because we already know that the velocity profile is a function of time, but this equation is not able to capture the capture the essence of the problem, that the one of the boundaries have a velocity profile that is varying with time. So this equation is like essentially wrong. So what it essentially wrong. Why? Because it's not able to capture the fact that the lower plate is oscillating. So it essentially tells us that let me try to show you. So it essentially tells us that there are two parallel plates. So funnily enough, the lower plate is now moving with some certain oscillating with some certain time plate. But what this equation tells us that the velocity profile that we will get after solving this equation is this. So even though the plate is moving, this equation tells us that the velocity profile would be of this form. So which is not the case. Right? It is not possible, right? So it essentially tells us that our governing equation itself is wrong. But now again, as we know that the governing equation that we chose, that is basically dou u by dou t is equal to nu dou square u by dou y square, was able to capture the flow physics in the limit where omega was less than mu by rho b square. Okay, so it was able to capture the physics when this was the scenario. But how the same governing equation cannot be how the same governing equation can be invalid when now we are changing the scaling, when we are changing the value of the parameter from this to this. Okay, so it essentially tells us that since the governing equation is not wrong, so governing equation would remain the same, right? The governing equation is the reversible equation that will remain the same throughout the flow field, and in general for every free flow problem, Newtonian free flow problem. So governing equation is not wrong. So what may be wrong is the scales that we have chosen to non-dimensionalize our governing equations. Okay, that may be wrong, right? So because for the previous case we told that the characteristic length scale is the entire gap between the two parallel plates. Okay, the characteristic length scale that we chose was this entire depth. So it might also happen that as I defined the characteristic length scale to be the length scale along which there is a considerable change in the flow parameters. So it might also happen that the flow parameters that are changing may not change throughout the length of this length b, but may be confined to a certain region within the flow field. Okay, it might also happen, right? Which is essentially the case of a boundary layer flow that we discussed while discussing flow through pipes. The viscous effects are confined within the boundary layer, and outside the boundary layer there is the flow is considered to be potential flow or indiscrete flow. So it might also happen like that. Okay. So it might have, so the scaling is actually the problem. It is being extensively discussed in the lecture of Vijay Gupta, but I don't think I will have enough time to know to tell you how it is important, why it is important. But just the conclusion that we get is that the scaling that we have done for the second case where omega is greater than mu by rho square is wrong. So we need to change our scaling. Okay. So that's why now we change our scaling in such a manner that we tell that there is a certain length or certain depth up to which the effect of the oscillation of the plate is felt, and beyond this depth the effect of oscillation of the plate is not felt, and essentially in this region the governing equation dvx by dt is valid. So that's correct. But within this region, also known as the boundary layer, this equation is not valid, and actually this equation itself has to be solved with different scaling terms. Okay, so that's the essence of the problem, right? The scaling is correct. The scaling that we chose or the governing equation that we got after scaling for this case is correct, but is valid only for the outer region or the region beyond the boundary layer, right? So within the boundary layer, again we need to take the same governing equation that we started with, scale the governing equations with different scaling terms, and then try to see which terms can be cancelled out or considered. Okay, so once we do that, we see that within the boundary layer the ancillary terms can be scaled as ancillary terms are scaled as rho L square del omega into V naught, where where del is the length or the length of the boundary layer or the thickness of the boundary layer. Okay. Also again in a viscous forces terms within the boundary layer now scales as mu L square V naught by del. Okay. And now since now after scaling we see that both these terms do not cancel out each other, and both of these terms had to be considered while solving the governing equation within the boundary layer. So that's why it is, as I mentioned here, within the boundary layer the viscous effects and inertial effects are significantly important and play their parts. So the ratio should be order of 1. Okay, since within the boundary layer both of these terms now cannot be cancelled out, because previously we saw that within the certain approximation, like if we consider this to be some value to be lesser than some certain value, then the viscous effects can be neglected, or within some certain limit the ancillary terms can be neglected. But within the boundary layer, since both of these terms are equally important, so the ratio of this parameter, basically the ratio of the ancillary force to the viscous forces, cannot be neglected. So the order of these ancillary terms should be equal to 1. So from that we get that the penetration depth has a delta has a scale as nu by omega, which is again same as the scaling of penetration depth that we obtained for a case where omega was less than mu by rho square. Okay. There also we got that LP scales as mu by omega. Okay, so but in this case just the difference is that del that would scale as mu by omega is not the entire domain but only a particular portion of the flow domain. Okay, it's not the entire domain but only a particular portion of the flow domain where the penetration or where the effect of the oscillation on the plate is felt, and beyond that region this region, which is essentially this region of fluid, does not experience the does not experience the effect of the oscillation of the plate, right? Essentially do not experience the effect of the oscillation of plate. So all the flow physics that is generated because of this oscillation of the plate is confined within this thin region that is known as the boundary layer. Okay, so that's what we wanted to conclude. So again, the velocity profile within this region is a bit again a tricky it's a bit tricky to solve, so we have not solved in this case. But what we essentially wanted to tell what wanted to convey was that how choosing different scaling parameters, right? Choosing different scaling parameters for the same governing equation for also for the same problem would result in different flow physics, right? Like for this case, like when we chose the characteristic length scale to be beta for all the for throughout the flow domain, we got a governing equation that was not able to incorporate the effect of the oscillation of the plate. So it essentially tells us that this governing equation, even though is valid from the viewpoint that the scaling is correct, but it was not able to incorporate the oscillation of the plate, right? The effect of the oscillation of the plate. So now what we did was we sorry, we looked into the problem in a different viewpoint. We thought that it might happen that the oscillation of the plate may be felt to only a certain depth or certain depth of the flow domain, and beyond which the effect of the oscillation of the plate will not be felt. So let us scale this depth as delta, some different length scale that would be different compared to the length scale that we initially chose. So choosing this equation now again resulted in a different governing equation. So that again gave us different different terms that were dominating the flow field. So that again resulted in different solution, and which will eventually, see if we solve the equation, will eventually result in a different velocity profile that would be able to incorporate both the effects of the velocity field within the boundary layer as well as outside the boundary layer. So that's what we need to know. And again there is a concept of singular perturbation and regular perturbation. So if I try to tell is that, so since the initial governing equation that we chose for solving was actually a second order differential equation, but after choosing a certain approximation, what we got was a first order ordinary differential equation. So now since the since the governing equation is first order, it won't be able to incorporate the effect of both the boundaries, right? It's quite obvious, since if the equation is second order, it would have two boundary conditions, right? But now since the governing equation has been reduced to a first order governing equation, it will not be able to incorporate the effect of both the boundaries. That's why this equation becomes invalid for the entire domain, right? But in a previous case, we saw that even if the ancillary term was cancelled out, the governing equation remained the second order governing differential equation, which was able to incorporate the effect of both the boundary conditions, right? So this is again the concept. So this can be considered as a regular perturbation problem. And this one, the equation that we got, so this one, the singular perturbation problem. I have not read entirely. So even from a mathematical point of view, the equation, like the moment that when we get the equation itself, we can tell that the equation, there's something wrong in the equation, because we started with second order equation, now we are left with a first order differential equation. How will it incorporate the effect of both the boundary conditions, right? So that's not correct. So that itself tells us that there's something wrong with the governing equation. Okay. So then there's lot of things to discuss. So I think this is out of the scope of this current discussion. So that's fine. Okay. So after that, now let me see. Okay, this again important, so we need to discuss it. Okay, so now we discuss about the role and Reynolds number flow. Okay, so again I'll try to move fast a bit so that I'm able to cover the entire content of today's session. So, but this part is very important. So I will try to be as I will try to go fast, but be as clear as possible, so that there is no confusion in it. Okay. So the role Reynolds number flow regime, it's by the name itself suggests that the Reynolds number in these types of flow are much less than 1. Okay? Or considerably very low. Okay. So the governing equation that we get after simplifying the Navier-Stokes equation with certain scaling parameters. So in this case, ideally we chose flow over a cylinder. That is the first problem that we chose. So the governing equation is exactly the same. So even after non-dimensionalization. So governing equation that we get is that this one, in the non-dimensional form. Okay. So now here. Okay. So now if we multiply this all the terms by Reynolds number, so we get this equation. So now if Reynolds number is much less than 1, okay, so what we are left is that Re dot St dou V star by dou T star is equal to minus Re by Reynolds number by Euler's number del star into P star plus mu star square by V star. Okay? So this is the governing equation that we are left with after we multiply after we multiply Re to all the terms in this equation and take the approximation that Reynolds number is much less than 1. So this term would go out, right? And also this term would go out. Okay. So we see here is that in this equation itself, this equation is again a bit more simpler compared to the initial equation that we chose. Why? Because, or I must say, significantly much more simpler than the initial equation that we chose, because we are now devoid of this notorious term, that is the non-linear term. Okay, so we are now devoid of non-linearity. So this equation is linear in velocity, right? So if we consider this as a source term, then it's basically a second order partial differential equation for velocity, where we consider this as a source term. Okay, it's a non-homogeneous equation. So since the equation is linear, we can apply the superposition principle, right? That is basically the sum of the simpler sum of the solutions would also be a solution, right? So this is the very principle of superposition. So that we can apply, right? So for this kind of these kind of flows are also known as creeping flows. So that's another term that we need to know. So that's why that is basically what is represented here. Okay. So this is a general formula governing equation. Again, like if we tell that this term is again much smaller than the value, or by the order of this term is much smaller than the order of these two terms, and again the equation simplifies further. It becomes steady, right? So that we are not taking into consideration, but if we consider general form of the creeping flow, general form of the governing equation of the creeping flow regime, and this is the general form of the governing equation, non-dimensionalized form, obviously. Okay, so just wait for 1 minute. Okay, so okay, there's not much to explain here. They're just given a solution that if you solve this equation for flow past a sphere, given that Reynolds number is much less than 1. So this is the velocity profile and this is the pressure profile. This is the pressure. Okay, this is how the pressure would be. So that's what they're representing here. So okay, so now there are some important observations that I wanted to say. So this is very important to understand the very characteristics or features of Stokes flow or low Reynolds number flows. Okay, so by their looks or by their names, they may seem very uninteresting or very boring, but it's not the case. the low Reynolds number regime has their own beauty. So that's what we are trying to explain here in these few points. Okay. Okay. So the first is that the flow pattern is completely symmetrical. The streamlines remain the same whether the flow approaches from the sphere from the left or the right. Okay. So let me just draw it here. So I guess it was discussed in the lectures, but still, what we're trying to say is the flow remains symmetrical. So this is the sphere. Then the flow in a Stokesian regime would be of this manner. There is some non-symmetrical nature in my drawing, but does not mean that the flow is unsymmetrical. So I'm trying to convey that flow would remain symmetrical in the case of low Reynolds number flow. Okay. So this is one of the characteristics. Okay. Even though the flow pattern is symmetrical, the pressure distribution is asymmetrical. Okay. This is another definition. So I guess the proper explanation has been given in the lecture. So I won't go dive deep again. So, but even if you just remember it, that's more than enough. So, and this is basically the pressure distribution in the case of flow over cylinder. Okay. The fluid velocity is significantly lower than the free stream velocity value V0 over a considerable distance compared to R. And also, like in the lectures, it was told that the V approaches 99% of the free stream velocity only when the radius is 16 times the radius of the cylinder. Okay, so if this is if this is R, but if we go 16 times this distance in the flow field, then only we will reach a point where the value of the velocity at that particular point will be 99 times the velocity of the 99% of the velocity of the incoming velocity field. Okay, so that's a very interesting thing and quite different compared to the case of high Reynolds number flow, where the viscous region or the boundary is much thinner than thinner. I mean, it's very thin compared to the case where the effects of viscosity is being felt in the case of a viscous flow. Okay, so it essentially tells the entire flow domain or the entire flow domain is being affected because of the presence of the sphere. It can be essentially be told as that. Okay, so this is what being explained here. This means that the effect of the presence of the sphere is felt over large distances. This is unlike the case of high Reynolds number flow. Because of this influence of the sphere over large distances, small particles moving at low Reynolds number interact strongly with one another. Okay, I guess it's quite pretty self-explanatory, since all the particles create a velocity field or create a disturbance that propagates to large distances. So if there are particles that are being mixed or dissolved in a highly viscous fluid, so all the particles will feel the effect of the surrounding particles because of their motion in that particular fluid. Okay, so that's what we are trying to say. Or basically there will be interaction between the velocity field or a pressure field that each and every particle generates. Okay, and this is now very important. Okay, the pressure difference near the sphere are of order 1 when scaled by mu V0 by d. Thus, the pressure difference is scaled as mu V0 by d, or the pressure forces scaled as the viscous forces. Okay, and see, I told that. Let me go back to this equation. I told that once we multiply Reynolds number to this equation, I told that since Reynolds number is very small, this term would go out, this would go out, and this term will go out because it's quite simple. Why? Because see, the scaling of the body force term would essentially be in a way that that would be large, I won't say very large, but large compared to the Reynolds number. Okay, and now if the Reynolds number itself is very small, then this term can be essentially be taken to be 0. Okay, and what we were left with is these three terms. Okay, so now the question may arise is that why was this term not uh, cancelled out? Okay, so see, so I told that if the flow is steady, right, let me go back. So if okay, see, if we take this term and say that if this term is very very small compared for a what to say, for a particular value, for particular value of velocity, then, and given that these terms are also of order 1, then this term, this unsteady term, can also be neglected. Okay, so obviously I'm just telling a very vague example. It's not obviously the case. We need to check how what are the terms or scaling parameters that result in the definition of the Reynolds number and the Struhan number, and how these parameters vary, and or in which limit I can take this term to be 0. But in most of the cases, like in most of the simplified cases, this term is again usually 0. So now we are only left with these two terms. Okay, so what essentially tells us that in a steady flow or in a steady creeping flow regime, the viscous forces are being balanced by the pressure force term. Okay, so now this pressure force term this ratio would only be of order 1, because this has no coefficient, so it essentially tells us that this scales as order 1. Okay, or I must say this scales as order 1. So this would remain in the equation if and only if this is unity. So if and only if this value of this coefficient scales as order 1. Okay, so it tells us that if we take this ratio now, so del P naught by mu V naught by D, so because we have taken the pressure to scale as this, so we will get that del P is mu V naught by D. Okay, so this scaling, what I try to convey is that this scaling is only possible if we assume that pressure scales as this, right? So it might also happen that, because in the case of when we are dealing with say when we are dealing with boundless equation, we saw many times that pressure may also scale as half rho V naught square, right? Which is not actually wrong. It's actually correct in the case where the flow is dominated by inertia forces, right? So this is correct. But if we consider same scaling in this case, in the case of Stokesian regime, then this validity that we have obtained, that RE by EU is order 1, then that fails to exist. Okay, then that becomes then this approximation becomes wrong. Okay, so this approximation is only valid when we scale or consider that the pressure forces would scale as a viscous forces. So the pressure would scale as a viscous forces. So that's why what I wanted to convey is that this pressure shows a very interesting nature. Okay, shows a very interesting nature. See, the viscous forces would always scale as 1 by R. So that's well defined. Okay, and again the inertia forces would scale as rho V naught square. Okay, it will scale as rho V naught square. These are well defined. But this pressure force, the scaling of this pressure force is not independent, right? It's not independent, like always the same. Like it will always scale as some certain value. Okay, it's not always defined. So what's the thing is that this pressure force always scales as the force, or the, I must say, the driving force, scales as a driving force in the flow field. So what it essentially means is that If the flow is governed by viscous forces, the pressure would scale as viscous forces. Okay. Again, if the flow is governed by inertial forces or is inertia dominated, then the pressure would scale as inertial force. So there is no true well-defined scaling for the pressure force term, but it usually scales as the force that governs the or that drives the flow field. Okay, so that's a very important conclusion that we get. So it's only because of that why we have not considered this term to go to 0. Okay, because if we would have scaled this as inertia forces, then this term would also have gone to 0. Okay. So that's why this is very important. That's what I wanted to convey. So that's fine. Okay. So okay. So this is again. Okay. So again, as I told that even for Stokesian regime, for Stokesian regime, this is actually the governing equation that we usually follow. Okay. And it's only after taking certain assumptions that the unsteady term can be neglected. So here is our example of some that unsteady nature of the flow field, where the unsteady nature of the flow field can be neglected. Okay, so here the unsteady nature of the coefficient is equal to this REST will be equal to d square by nu term, and this coefficient would be negligibly small compared to viscous terms when tau is much greater than d square by nu. Okay, basically if tau is greater, then basically this value is much less than 1, right? So if tau is much greater than d square by nu, then then this term can be easily neglected. Okay, so we take an example. So just an example, like for the case of human sperm, where the diameter of its head is 50 micrometer, swimming in a seminal plasma which has a viscosity of 10 to the minus 4 meter square per second. So d square by nu gives us 2.5 into 10 to the minus 5 seconds, right? So what it tells us that, so if the characteristic time scale for our analysis is greater than much greater than this value, then we can neglect the unsteady nature of the governing equation and only deal with this equation, which is much more simpler than the entire governing equation. Okay, so if tau is much greater than this value, then we can just neglect this term. Okay. So basically what they are trying to say, unsteady inertial term is significant only for times as low as 25 microseconds and may be neglected after that. So that's what we are trying to say. That was we are trying to convey. Okay. So how the quasi-steady nature of the flow helps us in neglecting the unsteady term and just deal with the steady force term. That's why the steady force terms, and that's why the name quasi-steady. Right? It's almost steady. Okay. So let me just see if we have time to cover the entire thing. Okay, let's take this example. Like these two examples are already discussed in the lecture by Professor Gupta. So I will be taking one of the examples since we are discussing about human sperm. So let us take that example itself. Okay. So the human sperm. Let us take the example. For human sperm with a head of 50 micrometer the diameter is traveling at 200 micrometer per second. This is the velocity. Okay. By moving its flagella in the seminal plasma with nu is equal to 10 to the minus 4 meter square per second, which develops a Reynolds number of 10 to the minus 2. See, since it's much less than 1, so we can consider it to be in the Stokesian regime. Okay. We are asked to calculate the length over which the sperm will coast if it stops moving its flagella. Okay, so it's telling that the sperm was moving with some certain inertia because of it has certain velocity, so it was moving with some certain inertia. Now, the moment it stops moving its flagella, so up to what distance would it go? Like if it is moving with some certain inertia, and if it stops moving its flagella, then up to what extent would the sperm move, right? So in our day-to-day life problems, like if we consider this case, like for example, like in car accidents, like if we strike a static object, what happens is that even if the car is stopped, the inertia of our body is moving, right? It's equal to the car's inertia when it was moving. So that's why when the car suddenly stops, our body moves forward the velocity with which it was moving. So what this question is asking is that, so if the sperm has stopped moving its flagella, because of its inertia, how much distance would the sperms move or coast, as they say in the case of liquid? Okay, so here the deceleration that explains is purely because of the viscous forces, right? Because there are no other forces in that particular flow field. So the only force that would result in a deceleration of the sperm is because of the viscous forces, right? The inertial forces of this sperm would be balanced by the viscous forces. Okay, so the deceleration is of the order, if we take F is equal to ma, which represents the retarding force. So ma could be scaled as rho s d cube as. Okay, where rho s is the density of the sperm and d cube is the diameter or the volume. We scale the volume of the sperm as d cube. Okay, so it's just scaling it. We don't need the exact formula for the volume of the sperm, but we just want to know how the volume of the sperm scale. Okay, so that's what we need. So this the mass scales as rho s d cube and acceleration scales as as, if you take that, and viscous forces scales as mu d v naught. We have discussed it time and time again, so I won't go again how we obtain this. So we get that the acceleration of the sperms or deceleration, retardation in this case, scales as mu v naught by rho s d square. Okay, so mu is the viscosity of the seminal plasma, v naught is the initial velocity with which the sperms were moving, and rho s is the density of the sperm, and d is the diameter of the sperm head. Okay, so the coasting distance, now we need to determine distance up to which this sperm will coast the moment the flagella, the moment they stop moving their flagella. Okay, so we know that as, or the acceleration, would scale as the velocity by time, and we again know time would scale as length by velocity. Okay, so we substitute the value of t here in this equation, we get as is equal to v square by l, or we get l is equal to v square by as. Now if we substitute the the value of as from this in this equation, we get that l is equal to v naught square mu v naught into rho s d square. If we cancel out this terms and we simplify the equation, we get that l by d is scales as rho s v naught d by mu. So here since this does not give any definition, because we think that it's a Reynolds number, but sperm itself is not a fluid, the density of sperm is not itself a fluid property, so what we do is we multiply and divide by rho f, so that we get rho f v naught d by mu, which then gives the density of the which then gives the Reynolds number for the fluid flow in the seminal plasma. So this gives us a Reynolds number, and we get so that we get l by d scales as rho s by rho f into the Reynolds number. Okay, and now if we take the assumption that the density of the sperm will almost be equal to the density of the seminal plasma. If we take it as 1, then we get that the length by diameter would the length up to which the sperm coasts upon the diameter of the sperm head scales as 10 to the minus 2, which would give the coasting length as 0.5 micrometers. So as you can see, it's very small. It's very small. We took the diameter of the sperm head to 50 micrometer, but the length up to which it coasts is only 0.5 micrometer. So it essentially tells us that the sperm would stop moving immediately after it stops moving its flagella. Okay, and also this approximation is also quite valid because, as we know, the sperms are like almost behave as a homogeneous the mixture of sperms and the seminal plasma almost behave as a homogeneous mixture. So it essentially tells us that the density of the sperms are almost equal to the density of the seminal plasma. Okay, so that's a very good approximation. So keeping that in mind, we get that's the conclusion that we get. And also from that what we get, from this what we get, conclusion that we get is that the response time for a fluid at very low Reynolds number to the motion of the boundary is practically instantaneous. Like the moment the boundaries stop moving, the fluid will stop moving, or the moment where the boundaries stops moving, the fluid will stop moving. So there's an instantaneous reaction to the movement of the boundary in the case of Stokes flow. You can also see this in the case of, if we consider this example. Okay, so assume that we are moving in water. So what happens is that while swimming, what we do is we thrust ourselves forward so that we could move ahead in the water. That's what basically swimming is, right? We thrust ourselves forward, like by flapping our hands so that we push the water backward so that we can move forward. Okay, so we need not need to do this flapping time and time again. So after we do a single flapping, we move a certain distance. Okay, we move certain distance, and after which only we again need to flap our hands or move our feet so that we can move again forward. Okay, but just consider a similar example, like instead of water, now you are swimming in honey. So I guess this example or this scenario is quite self-explanatory or you can understand it very easily, right? Now if you are asked to move in honey, you know that it will be very difficult for you to swim forward. Like it will almost be impossible to swim. Like you have to, like, I'm not saying it's completely impossible. It might happen if you are able to swim, but the forward movement or forward push that we got in the case of water for the single flap of hands would not be observed in the case of honey. Like the moment you stop moving your hands, you will be stuck or you will be stagnant in that honey swimming pool or whatever you say. So that's what being signified in this example, right? So I hope it was clear, and like these things like becomes seem to be interesting or very intriguing only when you try to imagine the scenarios, right? So I hope it was clear. So now we take a very interesting example. Okay, we consider the boundary layer theory. Okay, so this was not discussed in the class, but this I think is a very essential component of the approximate solutions of in fluid mechanics. So that's why I took this example. So again, I will just explain you the geometry. There are lots of things to understand in these definitions or concepts. I don't think I will have time to go through that, but let us just see how this example is somewhat similar to the case where we took the case of the oscillatory flat plate, like one of the plate was oscillating, that again resulted in generation boundary layer. So let's try to see that. Okay, So in this case, the question is that there are the governing equations for flow over flat plate. Okay, that is basically the boundary layer equations. Okay. So now what we do is we consider a flat plate, so basically this one, and we assume an incoming velocity with a certain value, that is u infinity. Okay, this is the free stream velocity. Okay, that is represented by u infinity. So once it approaches the flat plate, there is a generation of a boundary layer from the leading edge of the flat plate. Okay, the leading edge. So if this is a flat plate and this is the incoming flow, this edge or this point is known as the leading edge. Okay, and if say the flat plate ends at a certain distance, say here, this would be known as a trailing edge. Okay, trailing edge. We'll do one example, so that would be helpful, I guess. That is known as a trailing edge. Okay, so that results in the generation of a boundary layer. So here you can see that within the boundary layer there is a slowing down effect. So within the boundary layer the fluid experiences the effect of the place, and that's why a curved velocity profile. So the effect of the plate is being felt within this boundary layer, and outside it you can see that the velocity profile is essentially straight. So you can tell that outside this boundary layer the flow is essentially in viscid, or you can say that the flow is considered to be a potential flow. Okay, so this is what I'm trying to say. And this boundary layer, like the thickness of the boundary layer, if it is represented by delta, is not constant but is actually a function of x. So the boundary layer's thickness varies with the x direction, with the x coordinate. Okay, so there is a function of x. So the boundary layer thickness will vary along the x direction. Okay, so the coordinates are well defined here. So okay, so okay, so this is a very important point. Let me just try to explain it. So what I said when I said that the outer layer is inviscid, right, and the inner layer is viscous, so it does not mean that the fluid outside the boundary layer has no viscosity. Okay, it simply means that the effect of viscosity is not manifested in the form of shear stresses because of the lack of velocity gradients. Okay, so since we know that the shear stresses tau is defined as mu dou u by dou y. Okay, it's actually dou u by dou y plus dou v by dou x, but if it's one velocity one dimensional velocity field, then it's only one velocity component. So this is how the shear stresses are manifested. So the effect of the plate that would be felt by the flow would be manifested by the shear stress that is being felt or being experienced by the fluid. So if the shear stress itself is zero, it basically means is that the fluid does not consider or experience the effect of anything in the flow field. Okay, so this tau can be zero either if mu is zero or dou u by du by dy is equal to 0. Since mu is a fluid property, this can never be 0 and would be constant throughout the flow, right? Throughout the flow domain. This will not vary. It only varies with temperature. So this won't vary with space. So where the mu here would be equal to mu here. So it won't vary in the coordinate direction, right? So what can be 0 is the velocity gradient. So what essentially means is that since the velocity gradient at this point is 0 compared to this region, so that's why the fluid is not able to experience the shear stress that has been generated because of the existence of the plate in the flow field. So that's what it basically means to say. And within this boundary layer, the viscous effects are sustaining the shear stresses and transmitting the disturbance of the momentum from one layer to another. Okay. So I guess again this is very self-explanatory. So and again what is that? There are some assumptions that we need to take before solving these equations. First is that the flow is steady. Okay, this is for first assumption. Then we take rho to be constant, basically an incompressible flow, and finally we take it to a 2D flow. Okay, two-dimensional flow. We can again assume that the dimension along the z direction is very large, so any variation along the z coordinate can be taken as 0. So the flow is 2-dimensional. Okay, this is very important. Up till now, all the flow fields that we have considered or treated were essentially one-dimensional, so there was only one velocity component. But in this case, there are two velocity components, u and v both. So it's a 2D flow. Okay. So from the continuity equation, we get that dou v by dou x plus dou v by dou y is equal to 0. And this is now not equal to 0. Okay. So there is a velocity component along the y direction. However small it may be, but there is a velocity component. Okay. So so the Reynolds number here can be defined as rho u infinity L by mu. So u infinity would be the characteristic velocity and L is the characteristic length scale, and L is basically the length of the plate. Okay. So the x coordinate would vary as would scale as the length of the plate. U would scale as the free stream velocity, and y, the length along the y direction would scale as the boundary layer thickness. Okay. So if we do that, if we scale the governing equation, so we get that u infinity by del would scale as v infinity by del. Okay. If these two terms are since this is non-zero, this is non-zero, so the order of these two terms should be equal. So that essentially gives us that v infinity scales as u infinity del by L. Okay. This is the first conclusion that we get from the boundary layer analysis. Again, we make one further assumption, one more assumption. Okay, and this is essentially the approximation that we are going to make. Okay, so we made, if we were dealing with exact solution, we might have easily told that this term, like certain terms, this term are 0, but why they are 0, we do not really explain, right? We do not really consider. We just tell upfront that this is 0. But this is not the case in the case of approximate solution. So this is the approximation that we are going to take. So given the limit that del by L is much less than 1, because basically the boundary layer thickness is much less than 1, or much less than the the boundary layer thickness is much less than the length of the plate, then only our solutions are valid. Okay, then only the solutions are valid. Solutions are valid. The moment this approximation is not satisfied, all the equations, all the solution that we get from the boundary layer theory is completely invalid. Okay, so this is the approximation that we take. So this is very important. This is the approximation that we need to take for solving the boundary layer equations. Okay, so keeping that in mind, we do the order of magnitude analysis of the boundary layer equation along the y momentum equation for the boundary layer. Okay, so u would scale as u infinity. That's correct. V would scale as v infinity, and x would scale as L. Okay. Again, v would scale as v infinity, so it will be v infinity square by del. Right. So now pressure would scale as rho u infinity square. See, again, that's very interesting. Since the boundary layer flow are usually inertia driven flow, because the boundary layer is driven by the inertia of the incoming flow, so that's why now the pressure scales as rho u infinity square. See, there's so much concept to observe, right? Just the previous case we saw that our pressure was scaling as mu v naught by d. But now in this case, our pressure now scales as rho infinity square. Now if you substitute del P as mu v naught by d, this analysis again becomes invalid, or there will be some certain complications. So it's very important to know which are the scales that govern the flow field as well as the driving forces that drive the flow or that govern the flow. Okay, so it's very important. In this case, since inertia drives the flow, our pressure would scale as the inertia, as the kinetic energy. Okay, so pressure scales as rho u infinity square. Rho would be there and y scales as delta. Nu would be there, so v scales as v infinity, so it will scale as mu v infinity by L square. Similarly, it will scale as mu v infinity by delta square. Now, now sorry for the delay. Now now we look into this scaling of this term and see which of the terms are now dominating this y momentum equation. Okay, which other terms are dominant in the y momentum equation. Now if you substitute the value of v infinity here, which is basically v infinity scales as u infinity delta by l. So if we substitute this value, substitute the value of v infinity in this term, we will get that this will also scale as u infinity square delta by l square. Okay, so this both of these terms are significant, and this will scale as u infinity delta by l square. Now we look into this term. Okay, the new u v infinity by l square and new v infinity by del square. Now it's again quite self-explanatory, because since delta is much smaller than l, so and since delta is in denominator of this term would be significantly higher than this term. So this term can be neglected in this context. In this summation, this term can be taken to be 0. So this term is neglected. So now we need to check the relative magnitudes of the pressure term and the viscous term, and the pressure term and the inertia terms. Okay. So so we take the ratio of the inertia term and the pressure term. So what we get is that if we solve these fractions, we get that the inertia term and the ratio of the inertia term and the pressure term would scale as the square of delta by L. And since delta by L is much less than 1, it tells so this term so the inertia term is negligible compared to the pressure term. Okay, that's the first approximation that we get. So these terms can also be neglected. Now we again take now we again take the ratio of the viscous term and the pressure term. So once we do that, we get that the ratio of the viscous term and the pressure term gives us the Reynolds number. Ratio is equal to 1 by Reynolds number. And again we take that now we take one more assumption, that the Reynolds number is also large in the case of boundary layer theory. Okay, so right now it may seem that delta by L is being much less than 1 and Reynolds number being much larger than 1 or very large. These two may seem different approximations. Okay, so right now you can also consider these to be two different approximations. So first approximation that we took was that delta by L is much less than 1. Second approximation that we are taking is that REL or Reynolds number is much greater than 1. Okay, these are two approximations that we are going to take. Okay, just for now, but we will eventually see that these two are not independent but are actually interconnected. Okay, so keeping that in mind, so if we impose this approximation, so it essentially tells us that again that the ratio of the viscous term and the pressure term is negligible, so the viscous terms can also be neglected. So we are only left with the term that dou p by dou y is equal to 0, which essentially tells us that p is not a function of y within the boundary layer. Okay, within the boundary layer, and so there is no pressure variation along the y-axis in the boundary layer. Okay, so this is the first conclusion that we get from the y momentum equation after applying these two approximations. Okay, so again, x, y coordinates are generic and are called the boundary layer coordinates, and this analysis that we are doing is also valid for curved surfaces. Okay, are also very much valid for curved surfaces. And since in this case we are essentially telling that we are dealing with for a flat plate which can easily be solved using a Cartesian coordinate system, and that's why x and y coordinate system match or are exactly same as the x and y coordinates of the Cartesian coordinate system. But if now we are taking for an airfoil, these x, y coordinates will not be actually the Cartesian coordinates, that is the x and y, but will actually be the coordinates along the curved surface, or would be different from the x and y that we choose for a Cartesian coordinate system. Okay, so that will be different. and those will be termed as boundary layer coordinates. Okay, so this is what we need to keep in mind. Okay, so there's that. But now we look into the x momentum equation. Okay, again similar to the y momentum equation. Now we scale again, scale the each and every parameters and do the order of magnitude analysis of the each and every terms in the x momentum equation. So the the first term would scale as u infinity square by L. The second term scales as u infinity into v infinity by del. The pressure term scales as, again it scales as kinetic energy, so it will be 1 by rho u infinity square by L. And the viscous terms now scale as, the first term will scale as nu u infinity square by L, and the second term will scale as nu u infinity square by del square. Again, since L is much larger than del, so this term will go to 0. And again, if you substitute the value of v infinity in this term, you get that it will scale as u infinity square by L. And again, the pressure term scales as u infinity square by L. So here again, just 1 minute. Yes. So from this again from this we can see that the inertia terms scale as u infinity square by L, u infinity square by L. The pressure term also scale as u infinity square by L, and the viscous force terms scale as nu u infinity by del square. So right now we cannot just directly cancel out the terms, so because we won't get any significant conclusion of which term to cancel out. So we take that all these terms have similar order of magnitudes in the governing equation, right? So keeping that in mind, and also we do some further simplification. So since p is the only function of x in the p is only a function of x that we got from the y momentum equation. So this partial derivative can be converted to a complete derivative. So we will get dp by dx. Also, this dp by dx can also be taken as d infinity by dx, since pressure does not vary along the y coordinate. So we can take this pressure as the free stream pressure in the region outside the boundary layer. Okay, so that's fine. So with these approximations in mind, the final boundary layer equations are taken to be the continuity equation, that is dou u by dou x plus dou u by dou y. Then the x momentum equation that is being simplified, that is u dou u by dou x plus v dou u by dou y is equal to minus 1 by rho dou p infinity by dou x plus nu dou u square by dou y square. And finally from the y momentum equation we also get the dou p by dou y is equal to 0. And this need not to be written, but actually this simplification itself is an outcome of this equation. Okay, so these are interconnected, or basically this is the implication of the y momentum equation. So the assumption that we use is del by L is much less than 1 and REL is much greater than 1. So okay. So now these are the governing equations for the boundary layer for any kind of flow. Okay, for any kind of flow, for any kind of geometry. That's valid. Okay. But now if we take the given that the assumption that we took initially are valid, okay, are satisfied. But now since we are asked to find the governing equations for flow on a flat plate, we take that the outer stream or ingoing velocity field was given by u infinity, or was given by u infinity, right? So along the x direction. So now if we in the outer region or the irrotational flow region or the in-biscuit region, if we apply the Bernoulli's equation, that is p infinity plus half rho infinity square is equal to c, and disregarding the body force and this the potential energy term. Now if we differentiate this equation with respect to x, we get that dp by dx is equal to let me write it again. dp infinity by dx is equal to minus u infinity du infinity by dx. But now since du infinity by dx is 0, because u infinity is constant, so essentially tells us that deep infinity is also equal to 0, right? So our equation further simplifies to the momentum equation further simplifies to u dou u by dou x plus v dou u by dou y is equal to nu dou square u by dou y square. Okay, so this is the final momentum equation that we are going to use. Now what we get is that u infinity, this term, since both of these terms scale as u infinity square by l, and this term scales as nu u infinity by del square. So these terms, since both are existing in the equation, both of these terms should scale are of same order, right? So we compare these two terms, then we get that del square by l scales as nu by infinity. Now if we multiply L in both the sides, L to the denominator of both the sides, what we get that del by L square scales as 1 by REL, or del by L scales as REL or square root of the inverse of the or square, or del by L scales as REL to the power minus 1 by 2. Okay. So similarly, now if we take that del by L is much less than 1, we will inherently conclude that REL should be greater than 1. And since the boundary layer flow analysis that were eventually being designed were initially were designed for high Reynolds number flow. Like the boundary layer analysis is well established or well understood in the premise or in a scenario where the Reynolds number are quite large. So these are experimentally proven or experimentally analyzed. So Reynolds number is always considered to be large while doing boundary layer analysis. But this conclusion that we get is this is the conclusion that we get for the scenario when REL is much larger than 1. What I basically mean to say is that if we take the assumption that the Reynolds number for a flow over a flat plate or flow over any surface is much higher than 1, then the boundary layer thickness is bound to be very less. It is bound to be very less, or actually varies inversely, right? So if the Reynolds number is very high, the boundary layer thickness will obviously be very low. So this is the conclusion that we get. Okay. So let us do one example regarding this. So and then we will end today's session. So this is the example. Okay, a hydrofoil of 0.4 meter long and 2 meter wide is placed in a seawater flow of 12 meter per second, with rho is equal to 1025 kg per meter cube, and nu is equal to 1.05 10 to minus 6 meter square per second. Estimate the boundary layer thickness at the end of the plate. Okay, so in this case, if you are asked to determine the boundary layer, and there's also one point we need to know is that the boundary layer can be both laminar and turbulent. Okay, so and to see whether the which kind of equations to use to determine the boundary layer, we need to know the Reynolds number. So first and foremost thing that we need to do is determine the Reynolds number of flow field. So what we see is that the Reynolds number that we get is much higher than the transition Reynolds number or the critical Reynolds number. So we can tell that the flow is turbulent at the trailing edge of the hydrofoil. Okay, it is turbulent. So for turbulent boundary layer, this is the governing equation. Okay, this is the governing equation to determine the thickness of the boundary layer. So from that we get that delta is equal to 0.000712 meter. Okay, and this is being obtained. This relation is being obtained by the 1/7 power law, like the relation that we get for the velocity profile when we're discussing for flow in a pipe. Like for laminar flow it was a parabolic velocity profile, and for a turbulent flow it was a 1/7 power law that was used to determine the velocity profile. So similar thing we use, and we use the Karman's momentum integral formula to determine this equation. I'm just telling, it's good to know, but this is the equation for the boundary layer thickness. Okay, so after implementing that, we get that delta is equal to 0.00712 meter. Now if we take a scenario, take a condition that if the boundary layer would have been laminar for the same Reynolds number, okay, like it's not obviously it's not valid, because at that Reynolds number the boundary layer is bound to be turbulent. But say there is a scenario where we take that for the same Reynolds number, if the bond layer that developed on the hydrophile was laminar instead of turbulent, then we can apply the Blasius solution. This is a very popular solution, very famous solution, to determine the thickness of the boundary layer. It is valid for laminar boundary layers. Okay. So given that, we get that delta is equal to 9.35 into 10 minus 4 meter, the boundary layer thickness. Now, if we take the ratio of the turbulent boundary layer thickness and in the laminar boundary layer thickness, we get that the turbulent boundary layer thickness is almost 7.6 times the thickness of the laminar boundary layer for the same Reynolds number. So it gives us a very important conclusion that the turbulent boundary layers are usually much more thicker than the laminar boundary layers. Okay, so I guess that's enough for today. So if you have any doubt, I suggest that you put that doubt in the discussion forum, or if there might have been a bit a lack of understanding in today's session, I suggest that you attend the session in the next the other TA as well, and obviously please again look into the lectures of Professor Gupta. That would give you a very good understanding of the concepts. Okay, so thank you, and that's all from my side.